Hello, week 11. So our agenda today is we're going to do an example of carbon fiber reinforced plastic orientation for combined loaded stuff. Then we're going to start a new topic, which is introduction to metal cutting. We're going to look into orthogonal cutting, and then we're going to talk about process parameter and how mechanical behavior properties of material on selecting process parameters. Okay, so we're going to do carbon fiber. So we're going to go into example number 1. So it's about carbon fiber reinforced plastic orientation for combined loading. So what you see over here is a shaft, right? You see over here is a shaft, and this shaft has what we call a torque. What you see over here together with a rotation. So this is a torque because it's rotating, and then we have applied force of 800 and 800 over there. So what we want to do is this is we want to optimize the carbon fiber orientation based on the loading condition. Okay, so we're going to try to do this. So for this case, this shaft have a outer diameter of 1.25 inches and an internal diameter of 1.00 inches. Okay, so we're going to focus on element H. So over here you can see, right? So this is our element, right? So our element H. Okay, that's our element H. So I'm going to draw the orientation of our transformation. So this is one direction, vertically up. This is the other direction, and then we have one more going this way. Right, so these are our direction. So I like to call this my X. I like to call this my Y. I like to call this my Z. So if we look at element H from the plan view, right? We look at element H from the plan view. So this is X and Y, and then if we were to draw, so what we want to find out now, okay, is we want to find what is our stresses in the X direction. We don't know. What our stresses in the Y direction. We also don't know. And we want to find what's our shear XY, which is equal to the shear YX. And we also have not a clue what it is. So what we are looking at, this is element H. Okay, and the element H is viewed from XY. So based on this transformation, we are looking from the top. So if I were to put my eyes, okay, so these are my eyes, so that's why we're looking at. So that's how so we're going to find what is our stress x in the x direction, stress in the y direction, and stress z in the stress x and y, and the shear in the xy direction. So we don't know what they are. Okay, so if we don't know how to do. We cannot plot moment circle. Right. So the first thing we're going to do now is we are going to find the normal stresses. Okay, we can find the normal stresses. So we're going to view the shaft from the plan view. Okay, sorry, not plan view. We're going to view it from the side view. So I'm going to draw my transformation now. So view. I'm going to draw our transformation. So now we're going to view our shaft from the side view first. Right. So relative to this transformation over here, we're going to view at X in this orientation and Z in this orientation, and over here, right, this is your moment in your Y direction. Okay, so we're going to look at the moments to find the normal stresses. Right, so we draw our shaft. So we have, okay, so this is our shaft. So I'm going to make it a big. Okay, so this is our shaft. So our shaft, now viewing from the side, so this is our element H. So this is our element, right? So element H, right? So given that's the position, we can draw our reacting forces. So we have 800 pounds over here. And then we have another 800 pounds coming down. Okay. And we know the respective distance. So up to the edge of the shaft. So this distance is 18 inches. And from here to here, 10 inches. Right? And then we are going to assume, okay, so those of you who are not mechanical engineers, I'm fine with that. Okay, we're going to assume positive shear and positive bending moment. So what does this means is we're going to assume that we have a shear force coming down in this direction. Right? So this is our V at point H. And then we have a moment, right? So we have a moment at point H in that going at that direction. Okay, so M over here correspond to our moment at point H, and over here you have shear force at point H. Okay, so from here we're going to calculate our bending stress. Okay, from here we're going to calculate our bending stress. First, So our bending stress is equal to stress X. Okay, so stress in the X direction is equal to minus my over I. So all of this, so this is the formula where m, let me specify what they are. So this is a formula where m is the bending moment, and this will be in pound, inch, or Newton meter. Okay, and the definition of moment is equal to force multiplied by perpendicular distance. Okay, so the unit over here is Newton meter, and then we have y is a distance from the centroid to the maximum radius. Okay, to the maximum radius. Of the shaft. Which is in inches or can be in meters. Then I correspond to the second moment of area. Okay, and the unit is inches to the power 4 or meter to the power 4. Okay, so second moment of area, another term, is resistance to bending. Okay, we call the resistance to bending. So we have I is equal to pi over 4 multiplied by the outer radius to the power 4, and this formula is for our is for the, so you see this formula is usually for hollow solid shaft, and then for hollow shaft I is equal to pi over 4. Right, so R on the outside minus radius on the inside to the power 4. Okay, so this is for hollow shaft. Where RO is the outer radius and RI is the inner radius. Right, so we're going to start doing this. So we're going to carry out the first thing. We're going to do static analysis. right? So in static analysis, okay, so what do I mean by static analysis, right? So, but before we do static analysis, I'm going to copy this shaft. Okay, I'll just, so this is our shaft. Or let me copy, then save. You guys see me draw this again. Okay. So we are going to, paste. Alright. So we're going to do static analysis. Okay. So the static analysis is to find VH, the shear force at point H, and moment at point H. Okay. So what do we mean by static analysis? So in static analysis, just quickly recap. We have summation about forces in the z direction is equal to 0. Summation of forces in the x direction is equal to 0. Now, what this means over here, the first symbol over here, is you're seeing which direction is, like in z going up is what? Positive. In y going to the right is positive. And then summation about moment in the y direction anti-clockwise is positive. So you let all this be equal to 0. So that is what we mean by static analysis. So what we're going to do now is we are going to do positive that's going up, summation about forces in the z direction is equal to 0. So you have the 800s. So 1 is plus 800 minus by 800 minus by v at point H. So from here, you know v at point H will be equal to what? 0. Okay, so this is good news. So there's no shearing stress or shearing force acting on the shaft at point H. Then we do summation about moment in the y direction at point H is equal to 0. Okay, so we are going to fix this point, right? And then we're going to take the moment. So the first 800, so 800 times 18. Right, so this force, this point being fixed will induce a what? Induce a clockwise direction, so it's negative. Right, so plus by 800 times by 10. Right, and this with this point fixed is going in this direction. Right, so it's going in the anti-clockwise direction, so it's positive. The first one is multiplied by 18, is going in a clockwise direction, this is negative. Then you fix that point is going and moment about h over here at this fixed point is going in the anti-clockwise direction, so plus by mh. Everything is equal to 0. So what you see over here when you calculate mh, so moment at mh is equal to 800 times 18 minus, okay, so 800 times 18, so it's equal to 1440 or 14,400 minus by 8,000. So this will be equal to 6,400 positive 6,400 pound-inch, and it's going into an anti-clockwise. Okay, so this is positive. It's positive means this assumed direction is valid. If it's negative, then it's not valid. So what does this mean is this shaft, right, positive, this shaft, right, will bend this way because this end is fixed. Okay, so this direction is correct. So action equal to reaction over here. So this shaft, the overall deformation will look like this. Okay, so this is our deformation pattern. So what you see on this surface will go through what? Compression. And this surface over here will go through what? Tensile. Okay, I'll stop here. We'll come back to continue again. Bye.